Alright, hey guys, my research paper topic was Interactive Procedural Street Modeling. So let's get right into it. Maps and visualizing urban areas is required by many industries. It's very helpful for industries such as urban planning, obviously, when they're developing new cities or planning new residential areas. It's very helpful for them to visualize what the map would look like before they go and build it. However, to draw a map, especially one at such a large scale with 3D environments, is very tedious and time-consuming. So what the researchers came up with was the solution is to use computers to generate graphs of maps instead of manually drawing them. So the computer would procedurally generate a map for you based upon your input. So here's a photo of downtown Portland. This is actually a result of the research that they've done. It's not actually a real map of Portland, it's what the computer has generated based upon the inputs the user has put in, so that the result would look like and mimic a real map of Portland. So it's pretty good, it's pretty accurate actually, it's very similar to a real map of Portland, and it's a lot faster for the computer to generate it for you than for someone to manually draw it. So obviously, here's some background in terms of where it fits in computer science. There's the rise of technology, right? So we're shifting from paper maps to the digital age. Older maps are now considered forms of art, and it takes years and years of work for a cartographer to draw a one-to-one map. However, with computer vision and computer graphics, which is the category it falls under with the power of computers, we can now get the computer to procedurally generate a map for us with procedural generation techniques, and obviously there's the flexibility of user input to help sway or affect what the output would look like. So let's get into some industry background. First things first, the huge bottleneck is modeling bottleneck. All industries have this issue. When industry is trying to make a product of something, they want to visualize and make a model of it first before they commit to it, because often the ideas and the visualization of that idea can be different, right? But that's the bottleneck. It takes too long for people to draw maps, and the industries that require maps are things like entertainment industries, movies, games, advertisements. They might need city fly-throughs. You can think of the Spider-Man movie. Spider-Man's flying through Brooklyn or New York or whatever. The industry wants to generate a map of that and make 3D models of it, but that's the bottleneck. It takes a long time, so with computer generation they can get that map real quick. As I mentioned before, urban planning is another one. A real-world example, I guess, for us would be maybe Britomart train station. With the new train station that's been built in central Auckland, it could be helpful for them to generate what the new road and map layout of Auckland would be. So this photo here is one that a graphic designer has made of Auckland City with some road changes, I believe, the new one-way roads and things like that, and slow zones. But this could be very quickly and efficiently generated with a computer as well, instead of getting a graphic designer to draw it. You know, it's probably quicker for the computer to generate it for you. So some of the related fields would be construction and civil engineering are the two key ones. The one distinguishing factor though is scale. Civil engineering and roadworks construction, they're focused on maps that provide detail. They want to look at things like geological details, noise regulation, traffic density, vehicle pathing, soil density, legal details. Because safety to them and all this information when it comes to building the actual roads and houses is very important to them. However, from computer science, we just want to focus on the modeling and the visuals. We want to make the map look realistic, we want to make it look aesthetically pleasing. We don't actually care about any of these building details because we're just, visualizing the map. So there's a three-stage process that the researchers have come up with. The stage 1 is tensor field generation, stage 2 is street graph generation, and stage 3 is 3D geometry generation. This research paper focuses on the first two parts, tensor field generation and street graph generation, because there are multiple methods of 3D geometry that they use. They had mentioned they used one where they rendered 3D buildings in, but that's not the focus of this research paper, so I will be focusing on the first two parts here. And so the step 1 is inputting maps, and these maps are picture maps, so not actually like maps of roads, but pictures. So you can input a binary valued water map, which is a picture of like a lake or a river that goes through a certain body of land. It could be a height map that shows how high or how low the land goes. It can be a binary valued park and forest map, which shows greenery, so things like where parks are. And it could be a population density map P, which is a population density of streets. So I'm going to go into an overview of how the whole process, but before that we need to get into some math background. This research paper uses tensors, and the tensors in this research paper are referring to 2 times 2 symmetric matrices, so obviously it's a square matrix because it's 2 times 2. So yeah, square symmetric matrices in this form over here, as you can see, and where r is larger than or equal to 0, sorry, and theta is bound by 0 and 2 pi. So the definition for a tensor is it's an algebraic object that describes relationships between sets of algebraic objects in a vector space. It could be, these algebraic objects could be other tensors, by the way. Obviously, the tensors here are 2 times 2 matrices, and it's very hard to visualize what a matrix look like, visually, because they're just numbers, right? So to simplify things, you can think of them as points on a graph. You can think of every point as a tensor, or a matrix, and and the graph, sorry, is the picture or the continuous function of that picture of the water or the water map or the forest map. And then another thing we need to mention is eigenvectors. Eigenvectors are a non-zero vector that changes a vector by a factor, or scales it, I guess, and that scale or factor is the eigenvalue. Matrices can have eigenvectors, but it's hard to picture that since it's so hard to picture what a matrix visually looks like. So like I said, I'm going to go back to the whole simplified vector look. So if this arrow here is a vector, this longer arrow here can be an eigenvector because it's in the same direction, but it's scaled by, probably 3. It's probably 3 times longer. So that's just an example of a vector and eigenvector, but in this case, in this research paper, we're talking about tensors, which are matrices, but they're so much harder to picture, which is why I'm simplifying things down to represent them as vectors. So here's a whole process overview from step 1 all the way to step 9 that goes through all 3 stages, and I'm just going to briefly run you through so it sort of clears it up on how it works, and then we'll go into each step in detail. So step 1, in this case, they've inputted the water map, shows a body of land and like a lake or a river. Sorry, this is a river that goes through. Then step 2, this is the visualization of what a tensor is. So previous study and research has been done on visualizing tensors and matrices, and it looks something like this gray, like these gray lines, and I'll refer to that research paper further in this presentation. But basically, you can think of these cyan lines as tensors, and they look kind of like vectors, right? They're like long lines. So the user, this is interactive procedural generation, so the user interacts with the whole process. He or she inputs these tensors in here and bounds it by the river. So the next step after that, after the tensors have been placed in, the computer generates roads based on these tensors, and as you can see, based on where the tensors have been placed, the computer procedurally generates these roads. And as you mentioned here, most of the tensors are placed along the river here to bound the river, because generally you don't have roads on rivers unless it's a bridge. But as you can see here, there is one road that goes across here. So a bridge isn't really a factor in this research paper, but just by chance, sometimes the generation doesn't actually respect these boundaries, and it still generates roads that go across, which is why it's not 100% accurate. I just want to mention that out. Anyways, in the 4th step, there's a whole bunch of different tools. Because tensors are just matrices, you can change the numbers and modify these numbers, right, with maths to create different shapes. In this case, in step 4, the user defines a radial structure in this tensor field around in this area. And because of that, the computer, when it generates the roads based upon the tensor field, it reflects the circular radius structure, and the equation for this matrix is reflected in the road here. It makes a circular shape. Then in the 6th step, they're adding more tensors to define minor roads, like side streets. Later on, you'll learn that the side streets are actually represented by hyperstreamlines, but I'll go more into detail. For now, you just the user puts some tensors in areas where they want side streets, and then based on the hyperstreamlines of those tensors, that generates these side streets, like this, in step 7. And then in step 8, there are tools that you can use to modify these hyperstreamlines or these tensors to make the roads look more natural. In this case, they're adding noise to the roads, and this purple spot here and the red spot here in the radial area, and in this yellow red spot here, sorry, at these points. And what noise does is it makes irregularities in the roads. As you can see, before you add the noise in the top left, the roads look like this, which is not very natural, doesn't look like a road. But after that, this looks a lot better, right? It looks more like a road. Same in the middle circle here, it's a bit empty here, and then after adding noise and modifying the tensors, it looks like this. And step 9 is the final map, and then the last step, I guess, would be to do the 3D models and render in the buildings, but that's not the focus of the research paper. So yeah, there's the 1 to 9, and you get your beautiful map that looks like this. So now let's get into the details of each stage. So stage 1 is user inputs tensor fields based on inputted maps. So like I said, the map before in the example was a water map with a lake, so the user puts tensors around the border of that river, sorry, not lake, the river. Like I said here, tensors placed to follow coastline, because it's natural to design real roads to follow coastlines. And like I said, there are tools that you can use to modify tensor fields. So the regular shape, a grid shape, a radial shape. In that example, they used a radial shape. Back here, it's a radial shape, which creates a circle here. And from the math behind it, everyone knows, I guess, that the equation of a circle is something like in the form of x squared plus y squared equals, 47. That means the circle is centered at point xy with a radius of 7. X squared plus y squared equals 49. The circle will be centered at point xy with a radius of 7. And so, in terms of the tensors, they modify that tensor to create that radial shape by modifying the tensor mathematically like this. So this is tensor at point P is modified, the matrix is modified in this way, and this equation here looks very similar to the equation of a circle, and that's why it creates that radial shape. This is just the one example for radial. There are other ones that the user can input, which are predefined tensor fields. So you can set boundaries, like I said, to respect topography. So in the previous example, they set boundaries by the river, so that roads won't go over the river. Another example would be maybe there's a volcano or something. The user can put tensors around the volcano so that roads don't get generated over the volcano, because that's not really what happens in real life. We don't build roads on volcanoes. So here's some picture, for example. The top one is a grid example. So the photo right here on the far left, this is the visual representation of what the tensor matrices look like. And then based on these tensors, you can see it's kind of a grid shape already. The middle photo is what the computer generates. So based on these grid-shaped tensors, the computer generates grid-shaped roads. And this photo here is a real-life situation. This is a photo of a map of Brooklyn, New York, which is very grid-like. Then the bottom here is an example of radial. Like I said, by modifying the equation of that tensor at the point where you want the radial to happen, it creates a circle. And then this middle photo is what the computer generates, which is in a radial shape. And this far photo here on the far right is a photo of a map of Arizona, which actually has a real-world circular road. So this is pretty similar, right? It's pretty good. And then this is an example of the boundaries. So in this case here, this is the street view of what the computer has generated. By placing tensor fields along the coastline, the computer generates the roads like this. And this photo here on the right side is a real-world example of California Highway 1, which, as you can see, this one doesn't have the side streets yet, but the major road is bounded by the sea here, which is pretty similar to the real map. So next, after that, there are also other modifiers that we could do to the tensors. So you put the locally created tensor fields, which are the ones that user inputs, and then after that you can have modifiers. So there are 3 scalar fields, R1, R2, and R3, that modify the tensors. So the tensors have minor and major eigenvectors, which are basically more roads based on one tensor. Like if you saw it here, the user only inputted a few major tensors, but there's a whole bunch of eigenvectors, that are coming off these matrices that create all these other roads. And so by modifying them with the scalar fields R1, R2, R3, we can sort of bend them to create and replicate irregularities, because real roads have many irregularities. For example, there could be like a pipe underground that they want to avoid or something like that. Another thing we can do is we can limit tensor fields in certain boundaries. This mimics a brush tool. And let me just give you an example of that. So we'll go through the irregularities first. In this photo here, we've got a grid and a radial structure that has been generated by the computer. And by modifying the eigenvectors of those major tensors that the users put in, it creates bends. It makes those eigenvalues bend, right? Those eigenvectors bend, and this sort of replicates the bend in the roads, as you can see here. And with the brush tool, we set tensors. This purple line here are all points of tensors that bound this area. And we've set a whole bunch of tensors represented by the red one here, which is where we want all the other tensors in this boundary to follow. And so as a result of that, these conditions we put in, the computer generates roads that look like this. So all the tensors inside this area, their matrices properties are modified so that they follow this red tensor here, everything within this purple boundary. So this creates like a brush tool. You can paint in certain patterns of roads where you want roads to be. So step 2 is the street graph generation. So step 1 was all about creating a tensor field, which are points, I guess, of matrices. And based on those points of matrices, the computer generates a street graph view. And so in this example here, we've got a photo of a density photo. So white is very dense and black is not very dense. And so based on this photo, the street graph view makes very dense in the center and not very dense on the outside. And so now let's talk about hyperstreamlines, because hyperstreamlines are what represents side streets. So obviously it procedurally generates street networks from the tensor field, which is what I mentioned before, which is in stage 1 when we created the tensor field. Now we're procedurally generating these streets based on that tensor field. And hyperstreamlines are used from the tensors to represent side streets. So we'll go into what hyperstreamlines are in a sec, but I just want to say that this is based on the research of JOBARD and LEFER in 1997. They did a research on evenly spaced streamline placement, and so the researchers in this paper have modified JOBARD and LEFER's research to be applicable to modeling streets. So we've got to do some more math though. Firstly, tensor fields are a continuous function that associates every point to a tensor. Like I mentioned, every point on this graph, if you picture it as a graph, is a tensor. Every point is a tensor. And like I said, tensors have minor and major vectors, eigenvectors, sorry. These are not related to major and minor streets. And then a hyperstreamline is a tangent to an eigenvector field. Okay, so everyone knows what tangent is, right? A tangent, this red line here is a tangent. So every tensor, if you picture it as a vector, can have multiple eigenvectors that go in the same direction but different lengths, and each of these eigenvectors has multiple tangents at any point. You can pick any point and draw a tangent line on it, right? And so these tangent lines are hyperstreamlines. And hyperstreamlines are either major or minor. So now we've got this sort of hierarchy. We have 1 is the tensor, so we can pretend a point on this black line here can be a tensor. Then every tensor can have a whole bunch of major and minor eigenvectors coming out in the same direction but at the different lengths to represent other roads. And then from those eigenvectors, each of them can have a whole bunch of hyperstreamlines at any point. You can draw a tangent at any of those points. And these hyperstreamlines represent side streets. One thing I want to mention is orthogonality. Orthogonality means it's at 90 degrees too. Because each of these red lines are tangents, they're all at 90 degrees. Eigenvector is based off a tensor, and if the tensor is a main road, that means all the side streets are always at 90 degrees to this tangent, if that makes sense. And that's what it makes sense in real life, right? Because most side streets are at 90 degrees to main roads. So hopefully that made sense. I'm trying to simplify it for you guys, since it's hard to visualize matrices, which is why I'm picturing everything as points or vectors. So going back to JOBARD and LEFER's study on hyperstreamlines, their study was based on evenly spaced hyperstreamlines. So when the researchers directly incorporated that study, this is what it looked like, the photo on the left. All these side streets are hyperstreamlines, and they're all evenly spaced. So because of that, they're all not connected. They're all disconnected because they're all roughly evenly spaced. That's a problem for representing roads, because side streets are generally connected like this. So to solve that issue, the researchers basically modified JOBARD and LEFER study to connect hyperstreamlines until it intersects another eigenvector. So before, hyperstreamlines were evenly spaced, they wouldn't connect, but by extending it and increasing it until it intersects another eigenvector, we get this view here. So if you think of this here as the tangent or hyperstreamline of an eigenvector, we just continue its magnitude, or we continue its length until it intersects another point, and that other point is another eigenvector. And as a result, it connects all these side streets together like that. Another thing I want to talk about are other modifications to side streets or hyperstreamlines. There's a whole bunch of other tools. There's displacing, rotating, etc. of these eigenvectors or hyperstreamlines. But the one noteworthy one I'll talk about is seed point creation. So it's similar to like seeds in random number generators. You can have like in Java like a new random number, and you can random.setSeed. You can give it a seed so that the random number is within a set value or a set range. So everyone with the same seed gets the same number. That's kind of similar with how this works. In this case, we've got a map of Chicago on the left. This is a real world map of Chicago. It has this diagonal road going over it. And so with the random generation, what you do to replicate this diagonal line, this photo on the right here is what the computer generates, is you set a seed point, for example, bottom left here, and you set a seed point, for example, top right here, and then the computer would generate a hyperstreamline that goes between these two seed points to sort of overlay this road to replicate this curved road in Chicago. So here's the examples that I'll go over to maybe hopefully clear it up for you more. In step 1 here, we've got a removed hyperstreamline. So this is a side street, as you can think of it as that the hyperstreamline is a tangent. We've simply removed it, so we just don't draw this tangent to this main road, and this main road is a tensor or eigenvector. We just don't draw that tangent, and as a result, we don't get this side street. Step 2 is we edit it. In this case, we just change the magnitude or the length of that tangent, or hyperstreamline, so that it's cut short. And step 3, we're displacing it. Not all roads straight, right? So we modify it by an angle, or r, those constants I mentioned before, and as a result the tangent is curved. I guess by definition it's not a tangent anymore, but that's why they're called hyperstreamlines. So that way the tangent is curved, or the hyperstreamline is curved, so the side street here is curved. And with a combination of these tools, modifying the tangents and modifying the hyperstreamlines and eigenvectors, we can replicate complicated roads. So here's a map showing the cracks in Missouri. So the roads in Missouri in America look very like cracked, they look like cracks. And so by a combination of removing hyperstreamlines, editing hyperstreamlines, displacing them, rotating tangents and eigenvectors, sorry, not tangents, tensors and eigenvectors, we can replicate these sort of cracked patterns in the roads, as we can see here on the right side. This is what the computer has generated. And yeah, and the last step, I guess, is the modeling, the 3D modeling, adding the building, sorry, but that's not the focus of this research paper. So some discussion. Because of this research, it's now possible for us to procedurally generate maps with user input that replicate real-world maps. They're very detailed and realistic, I guess, and it's done fast because the computer generates it for you based on a set of inputs that the user has put in. It is based on the previous research done by JOBARD and LEFER on hyperstreamlines, or evenly place type of streamlines, and it was also based on the visualization of tensors. So WIJK 2002 and Zhang in 2007 both did research on tensor field visualization. So because of these past researches, it is possible for these for this procedural generation of maps, I guess, to be possible based on these past research. And in the future, this research can aid similar fields of procedural generation, such as fractal patterns, plants and leaves, modeling of cracks, bark and crystalline structures. They're all quite related. So here's some future. So with the software, obviously, and the research done here, we can make maps that are detailed and realistic. The pros of it is that it's very, very realistic. It looks like real maps. It's fast and efficient, like I said a lot of times. It's modifiable because the base is a tensor field. They're all like matrices and numbers. We can modify these numbers in the matrices, and as a result, the changes will be reflected in the street view. That's the advantage over graph-based software, because in a graph-based software, if you make one change to a road, you've got to redraw all the roads around it. But because here we're using a mathematical base of these tensor fields, making one small change, the math will, make all the changes for you. And it's obviously flexible because of user input. And the con is that it's only single level spatial resolution. Basically everything is in the same scale. We can't modify a tensor field at different scales. We can only represent it at a building and road scale. And obviously it's a replica, so it's not 100% accurate. So one of the improvements that the researchers did mention is they want to add more levels of spatial resolution. So instead of having one tensor field, they could have multiple. So one tensor field represents the roads and the buildings. Then they could have a second layer of tensor fields, which could represent smaller things such as trees and cars. Obviously that complicates the algorithm, but that is one improvement that they're looking to do in the future. And so yeah, thank you. That's the end of the presentation. I'm just going to show you some final products of a downtown map for Taipei. This has been generated through this research through interactive procedural street generation. If you compare this to a real world of downtown Taipei, it would look very, very similar. And then here is the obviously one after you put 3D modeling. This is not downtown Taipei, this is just a fake virtual city, but you can picture this being used in entertainment and gaming industries or advertisements and things like that. So yeah, thank you.